Okay, these are Unit 14, Day 2 notes on limits. So this is talking about limits as x approaches infinity. So kind of a helpful acronym to help remember is BOBO, BOTN, EATS, DC. And this is actually the same acronym you can use to do horizontal asymptotes. So what BOBO stands for, bigger on bottom 0, BOTN, bigger on top none, EATS, DC, exponents are the same, divide coefficients. So my three things are, degree of the numerator is greater than the degree of the denominator, the limit is 0. So that's BOBO. Bigger on bottom, 0. Because it's bigger here. It's power of 6 versus power of 2. Degree of numerator is greater than degree of denominator. It does not exist. So that's bigger on top, none. Bigger up here. It's squared. Down here it's just to the first power. And lastly, the degrees are the same. X to the third, EATS, DC. Exponents are the same, divide coefficients. So you're dividing coefficients of the part where it's the same. So x to the third has a 3. X to the third down there has a 1. So 3 over 1 is 3. So here, it's bigger here. So I like to highlight to point out like exactly where they are. Bigger on the top. That's 2, that's 1. Bigger on top, none. Does not exist. X to the 1, x to the 1. Exponents are the same. Divide coefficients. And the coefficients are 1 and 1, so it's 1. Here I have power 1. Here I have squared, so it's bigger on the bottom. BOBO, 0. Here, this one's a little bit tricky. I have a square root. And I'm taking the square root of this. But I really just care about the first term. So I really just care about 4x squared. The square root of 4x squared is 2x. Then I can see the exponents are the same, divide coefficients. And the square root of 4 is 2, and that's 1, so it's 2. So again, these abbreviations, this BOBO, BOTN, EATS, DC. The bigger on bottom, 0. Bigger on top, none. EATS, DC. Exponents are the same, divide coefficient. It's only when the limit approaches infinity. So if you notice, I have infinity or negative infinity. So it's not like approaching 5 or 6. It's only for approaching infinity or negative infinity. So again, BOBO, BOTN, EATS, DC. Bigger on bottom, 0. Bigger on top, none. EATS, DC. Exponents are the same, divide coefficients. Only when it's approaching infinity or negative infinity. Okay, next part of Day 2 notes is one-sided limits. So we talked about we can't have a limit if it's not the same from the right and the left, but we can have one-sided limits. We can just say the limit as it approaches from the right or the limit as it approaches from the left. So if I look at this graph here, I can see, okay, I definitely, right here, it's not the same coming in from the right or coming in from the left, but I can have a limit from the right and from the left. So if I look at this is at 1, so it's down here. As it approaches 1 minus, so that means from the left. As it approaches from the left, it has a minus after, it's coming from the negative side. You can see as it approaches from the left, it's approaching 4. When you see a plus after it, that means approaching from the right. So as if I follow it from the right with my pencil or pen, it's approaching negative 2. Then I can compare those and say, okay, they are not the same, so the limit at 1 does not exist. But again, the limit 1 from the negative side exists, 1 from the positive side exists, but they're not the same, so limit at 1 doesn't exist. If you look at 6, as I come in, follow my pencil, from the right, it approaches 5. Follow my pencil from the left, it approaches 5. So this one, the limit exists. It is 5. And the fact that I have a dot down here doesn't matter, right? There's a hole, but we said I don't need to have an actual point right there. The function saying f of 6 is not the same as saying the limit, right? F of 6 is actually 2. This is where my dot is. F of 6 is 2. But the limit as x approaches 6 is 5. So again, just because my f of 6 is not the same as the limit doesn't mean there's no limit. So here again, the dot is here, which means f of 6 is 2, but my limit my limit as x approaches 6 is 5. So if I want to know if the limit exists, I need to see, is it the same from the left and the right? And if it is, it exists. So if I have a piecewise function, I'm going to have to plug it in. So this right here, I'm looking, does a limit exist as x approaches 0? That's what this number here is for. So I plug 0 in, and I see, is it the same? So if I plug 0 in here, I get negative 1. If I plug 0 in here, I get negative 1. So yes, the limit exists, and it is negative 1. Same thing here. Does a limit exist as it approaches negative 1? Well, plug it in here, plug it in here. Are they the same? It's 4, so yes, they are the same, it exists. Now this one, you can see it's a little bit trickier. There's 3. So you got to think about which 2 am I using? As x approaches 2 from the positive side. Well, it's definitely not this one, because this is from the negative side. I have greater than 6 and between 2 and 6. Well, I don't want to use this one, because this one is not right before the 2. I actually want to use these 2. So this is the one I'm going to use from the positive side, which means it just equals 2. I don't even have to plug anything in. From the negative side, when I plug 2 in, I get 4. They are not the same, so the limit does not exist. Same thing with this one on which 2 to use. I want to know, does a limit exist at 0? Okay, so less than 0, that's easy. This is my left side. So I have 0 minus 3 is negative 3. But then which one do I use for the right side? Well, I use this middle one, because this is the one that's right before 0. I want to know what happens right before it hits 0. And this one is not right before, but this one is. And it's negative 3. So negative 3, so yes, the limit exists. So that is pretty much a summary of day 2 notes. Is recognizing that you can have a right limit and a left limit, and they can both exist, but if they're not the same, then the limit doesn't exist at that point.